Let me welcome everyone to this week webinar with the presentation by Todd B. Walker, who is Associate Professor of Economics at Indiana University. His research interests include macroeconomics, econometrics, and financial economics. Professor Walker has made important contributions to the analysis of fiscal issues, especially to further our understanding of fiscal foresight and debt limits. And he has also developed techniques to study dynamic models with asymmetric information, and very generously he has made many of these codes available for researchers to use. Professor Walker earned a BA and an MA degree in economics from Miami University in his native Ohio, and a PhD in economics from the University of Iowa. So without further ado, let me welcome Todd Walker, who will be talking about approximate aggregation in the neoclassical growth model with idiosyncratic shocks. Thank you very much, Todd.
Thank you, Alberto. It's a pleasure to be with you, and I appreciate the opportunity. This is a unique opportunity for me. I hope everything goes smoothly. So this is joint work with Nets Katz, who is a mathematician, and Karsten Chipaniuk, who was a mathematician, is now becoming an economist. He's a PhD student here at Indiana University. And I met Nets several years ago, and Nets had an interest in economics. And Karsten was a student of Nets. And so when Karsten wanted to transition over to economics, I said the easiest way to do that is just to work on a research project. And so that's what we did. This paper actually is very preliminary. We have, I think, some interesting results that I'm going to present today, but there's still a long way to go. And what we're really interested in is aggregation in a very standard neoclassical growth model that features idiosyncratic shocks, idiosyncratic labor shocks. And this is a workhorse model. So this is, again, a standard model that you learn in your first year of macro theory. And it has idiosyncratic shocks to labor income that's going to generate incomplete markets. And incomplete markets are going to lead to aggregation issues. And what we do in this paper is we try to provide an explicit characterization of what's called approximate aggregation. I'll define that more carefully in a few slides. But the explicit characterization is going to allow us to make this kind of important connection, I think, between an important paper by Crucell-Smith and a well-known paper by Arigari. And so I'm going to do two things today. I'm going to talk about approximate aggregation, but I'm also going to talk about kind of this deep connection between Crucell-Smith and Arigari that maybe people have missed, maybe they don't, I'm not sure. The other thing that we do in this paper that's a little bit unique is we provide what I'm going to call a binning argument. And the way that you should think about approximate aggregation is that we're going to put agents, so there's going to be heterogeneity in terms of labor types, but we're going to be able to put these different households into different bins. And within each bin, you're going to have approximation. We're going to have an aggregation holding within each bin. So you think about if there are 5,000 agents, what's the minimum number of bins that you can get away with and still approximate the economy accurately? So that's how you should be thinking about these bins. And of course, I'll give you a lot more details in a few slides. Why is this important? I think heterogeneity is becoming more important every day. So there are a lot of new papers, there's new literatures on why redistribution is important with respect to monetary and fiscal policy. One of the key questions of this literature is really Lucas's cost of business cycle. So Lucas has this kind of famous back of the envelope calculation where he showed that business cycles are not that costly. And within the framework of a representative agent economy, that's very easy to see. Within the framework of an economy where you have heterogeneity, the cost of business cycles could be very costly to those who are maybe not as well off as others. I think this a really hot topic. Policy makers to be thinking about in terms of how you about monetary and fiscal policy. But how that's viewed, wealth and wealth. I think that this is a really important problem to solve. The mainly a theoretical paper. That much heavy mathematics. In the paper. Um, with a computation. Computational result model. Really laid the for setting up a whole computational models with heterogeneity. In fact, there's a special issue devoted solve model on a and there's several really nice papers in there that basically walk you through and we're trying to argue a lot of this model. What we don't know the to catch up in terms of advancing the theory to catch up with the computation. The other thing that I'm going to briefly mention is that we're also working on the computational aspects of this problem. And we believe that if you improve the theory, that could lend itself to better numerical analysis. This is something that we just started only a few months ago. We'll make a lot more progress hopefully over the summer. But I'm going to tell you a little bit about how this binning argument that I briefly described earlier is going to lead to hopefully better and more improved numerical methods for solving these models. So I'm just going to really jump into the model, and I'm only going to talk about basically these 2 points. I'm going to show this kind of deep connection between Krusell-Smith and Arigari, and then I'm going to talk about our theorem of aggregation within the context of this kind of very simple model. So time is discrete and finite. We're going to think of it as a cat T model, but you can take the limit as T goes to infinity without any trouble. There's going to be a representative firm with Cobb-Douglas production technology given by the equation you see there. ZT is going to be an aggregate technology shock, which is going to play a really important role. KT is going to be capital. LT is going to be labor in the usual notation. And you see that KT minus 1 is going to enter the production function at time t. We're going to assume that markets are competitive. So you have the real interest rate wage rate being equal to just the marginal product of and capital. So in here. The household side is where things get a little bit more complicated, only slightly more complicated. They're going to be capital N households that are going to be indexed by J. They're going to live for T periods. So it's not an overlapping generations model. It's just these households are all going to live for T periods. They're going to get this idiosyncratic shock to their effective labor units. So this CJT is going to be some random variable between 0 and 1. So you have 1 unit of time. And each period you get hit with this CJT shock that tells you how many units you're going to supply to the labor market. In this version of the paper and the talk, we don't have labor in the utility function, but we can easily do that. That's not going to be an issue. What I am going to do is think about this effective labor unit shock as this EJT. This EJT is going to be the share of the aggregate wage bill that goes to household J. So I'm transforming this kind of effective labor unit shock into a shock that tells you how much of the aggregate wage bill household J is going to get. And it's going to be a share, so you can think about the EJT as being CJT over the sum of CJT over the sum of household J's. What I'm going to assume, and this is not going to hold throughout the talk, but we can relax this assumption, but we're going to assume that there's going to be some positive probability of unemployment each period. If you have positive probability of unemployment, borrowing you have to count. Holdings. Things that I'm talking about. I can write the house constraint as consumption J given by wage bill. This WT again, this J T is share of I'm going to get some return R holdings minus 1 And there's going to be some appreciation. Rate. Delta. For most of the talk, I'm going to assume that is equal to 1. And I'm going to argue that this is crucial. For the aggregation result, or so
You mentioned that uh,
if you have an unemployment the probability of unemployment is period. Then you have positive amounts of capital each period. So that's the household's budget constraint. And this is the extent of the model. I mean, it's a very simple along some dimension but it's very complicated along other. Utility standard utility. So we have uh, it's going to be log when the sigma equals to 1. And for most of the talk, I'm And just appreciation, our results are going to carry through whether you have log or whether you have something uh, uh, different from one. So you have CRA coefficient. Here is again relative that I want to talk about is establish this deep there's a question mark. It's not that deep. Um, people have argued that there's a very subtle between Smith and Arigari, and I'm going to show you, at least try to convince you that that distinction is actually not all that crucial. In fact, there are parameterizations in which the decision rules of Krusell-Smith are exactly the same as Arigari model. So this is the first result that I'm going to derive. So when Krusell-Smith came out, they said, adding this aggregate shock to an Arigari model is non-trivial. And I'm going to walk people through kind of why this is non-trivial, because I think this is a crucial point. It's non-trivial because now agents have to keep track of this cross-sectional distribution of asset holdings at each date t. That becomes a relevant state variable. So those of you who know the Krusell-Smith model know that this is exactly what causes trouble when you try to compute equilibrium. And so you have this, you just add this aggregate shock, and that's the Z shock that I showed you earlier. So this is the Z shock that hits the aggregate production technology. Now what has to happen is the agents of the model, in order to formulate forecasts of interest rates, they have to keep track of the asset holdings of each agent. So now there's a cross-sectional distribution of asset holdings that are going to be relevant for me when I make my investment savings, investment consumption decision. So I think I'm going to talk a little bit about Krusell-Smith, and I think there are two contributions. The first one was computational strategy, which I'll talk more about later. The second one is this approximate aggregation result. So how do you think about this Krusell-Smith setting? Well, this is the textbook treatment in Lindqvist and Sargent. And this is how the textbook treatment of Arigari models is presented in Lindqvist and Sargent. So the household, this lowercase k is going to be the household's capital stock. This E is going to be their employment shock. This is their value function. So they're going to max by choosing capital stock tomorrow, consumption, and you can see here that the expectation is going to be with respect to my employment shock process. And my budget constraint is just going to be equal to my consumption capital tomorrow plus my interest rate. And here the notation I think is really kind of important. The notation is that the interest rate depends upon big K and big capital N, which is, I'm going to use capital L, but Lindqvist and Sargent use capital N for the aggregate labor. So my interest rate depends upon the aggregate capital stock and the aggregate amount of labor supplied. So does the wage rate, because these are just the first order conditions from the firm. And what I need here is I need kind of a law of motion. So I'm going to try to do this. It's not working. So I need a law of motion for the aggregate capital stock. So there's something kind of screwy going on with my picture. I don't know if you guys can see it too, but as I take the cursor over, I can white out some of the equation. Let me see if I can do this. So the aggregate capital stock is just going to be, I'm just going to integrate, or you can think about it as summing over all the households, and this lambda is going to be the distribution of wealth, which is going to be a function of my capital holdings in my employment shock. And so I'm just going to integrate out to get aggregate capital using that equation with the green arrow. Now, how is this different in Crucell-Smith? So Crucell-Smith, you can see that now the state variables contain not just my capital holdings and not just my employment shock, but also this distribution of wealth and the aggregate technology shock. So this distribution of wealth becomes a relevant state variable, and you can see how the problem changes. The budget constraint is basically the same, where I have to keep track of the aggregate capital stock, labor, and now it depends upon the technology shock. But what's different is I have to have a law of motion for this distribution of wealth, and that's what this star equation is here. So the star equation is the law of motion for the distribution of wealth, and now it's going to evolve over time because of my aggregate technology shock. Because of my aggregate technology shock, this is going to evolve over time. So I have a question here that says aggregate supply in is endogenous. How? So it's not going to be, so in this model, I don't have a labor leisure choice. I'm just going to have, everyone's going to get hit with this idiosyncratic labor shock, and they're just going to supply that amount. And they supply that amount, and that's going to determine my interest rate and my wage rate. So this is going to be how aggregate supply is determined, how aggregate labor is going to be determined. Don't know if that answers. Okay, thank you. And so what really is crucial here is this starred equation that I have this arrow over, which is telling you the law of motion for the distribution of wealth. And you can see that the only difference between this economy, the Aggregate economy and the Crucell-Smith economy, is the aggregate technology shock. That's the only difference. And now, because of the aggregate technology shock, you have a time-varying distribution of wealth. You have to keep track of that. As you increase the number of households, this distribution of wealth becomes really big. And so the state variable becomes really big. And so this is really the problem with adding an aggregate technology shock to Aggregate. And what Crucell-Smith have done is they kind of contrived a computational strategy to solve this model. And here's the computational strategy. So here I just have what's the difference between these two slides. So this slide and this slide is that I took the Crucell-Smith setup, which is here, and I moved it up here. So this is the Crucell-Smith setup up here, and this is the computational strategy. So they have to have this law of motion for the distribution of wealth. And what they do is they guess that the law of motion for the distribution of wealth, or the law of motion for the aggregate capital stock, is just going to be linear in logs. And I'll show you. So that linear in logs just means that if you had, so let's say you're taking macro theory 1, which I give this problem out all the time. So you're taking macro theory 1, and you have to do a guess and verify of a value function problem. Well, what you do is you give the students the neoclassical growth model with log utility and complete depreciation of capital. And you can do a paper and pencil solution to this model. And the paper and pencil solution is exactly this guess right here. So you guess that the log of the capital stock is just depends upon, so this prime notation is the capital stock tomorrow. It depends upon just the capital stock today in a linear fashion. And so this is really the guess that you would make in your macro theory 1 course. And this is the guess that Crusoe and Smith first applied, and then they showed that it was actually a good guess. And the way that they did that is they just added higher moments. So they added the log of capital, the whole thing squared. They added the log of capital, the whole thing cubed. And they showed that those additional moments were not important in terms of helping me forecast tomorrow's capital stock. So you can kind of see what the problem is here. The problem is that the agents have to forecast tomorrow's capital stock in order to figure out what the interest rate is and the wage rate. And so they need a law of motion, and Crusoe and Smith are just going to give them this law of motion that's basically saying what matters is the first moment of the distribution of wealth. Okay, and so what I'm going to convince you of is that this guess actually, to my knowledge, the best of my knowledge, no one has really shown that this guess is the correct guess. This is all kind of computational. And what I'm going to argue is that under certain parameterizations, it's very easy to show that this is actually a really good guess. So why is this such a good guess? What I need to do to prove this, K is independent of N. So if I were to have non-separable utility, so the question is, why is K independent of N intuitively? If I were to have non-separable utility, it definitely wouldn't be. Here, the labor-leisure choice is just going to be intratemporal. So the intuition is that you have an intratemporal decision of labor-leisure, and you have an intertemporal decision of the capital stock. But this capital stock is definitely not going to be independent of the allocation of the employment shocks, if that's the question. So the employment shocks are definitely going to play a role in my aggregate capital holdings. But what this guess assumes is that you're exactly right. This guess assumes that these things are independent. But again, this guess hasn't really been verified analytically. So that's one of the things that I'm going to try to do. So the important thing that I'm going to take some time with is I'm going to reformulate this economy in terms of shares. And this is a very simple kind of algebraic thing to do, but it's also really crucial for deriving our results. So I'm going to reformulate the economy of shares. So this is just the production function, right? And I know that I can write this as, so this is the first order condition. This is my interest rate. This is my wage rate. And because it's Cobb-Douglas, I can write this as the return on the share going to capital is just equal to alpha times YT. The share going to labor is just 1 minus alpha times YT. Right? So what I'm going to do is reformulate the economy in terms of shares of output. And this first order condition from the firm is going to tell me that I can just write capital share and labor share as just some fraction, alpha and 1 minus alpha, of output. I'm going to define capital omega as the share of aggregate resources that are saved in period t. So you think about this as yt times capital omega t is equal to capital KT. So omega t is a share of resources that are saved in period t. The choice variable is going to be this SJT of the household. Household J's share of aggregate investment is going to be labeled as SJT. This is also a share. So these are shares. And what I'm going to do is, for most of the talk, suppose that you have complete depreciation of capital. Now, I'm going to argue that this doesn't really matter for aggregation. The reason why it doesn't matter is if I can get aggregation with complete depreciation, I can definitely get it when delta is some number less than 1. And the reason is that this is going to give me a lower bound for aggregation. If delta is some number that's less than 1, my return to capital holdings is going to increase. And what I'm really trying to fight here is I'm trying to fight an incomplete markets assumption, which I haven't talked about yet. But I have some uncertainty in my employment. I have to have precautionary savings. I have to hold capital stock in order to kind of combat this uncertainty in my labor outcome. If I have a higher return to capital, this is going to be easier to do. So delta equals 1 is actually a lower bound for the aggregation result. So it's working against us, but we're going to impose that assumption for most of the talk. I'll show you in a few slides that it's not going to matter. So this is really kind of a crucial slide. And this is the budget constraint of the household written in terms of shares of output. So I've kind of gone step by step here. So I've written this as, this first term is my share of aggregate wage times the aggregate amount of labor. So this is my share of the aggregate wage bill, this EJT. This is my return to capital holdings. And this is my savings. And what I'm doing here is I'm just using a little bit of algebra to show that I can write this as a share of aggregate output. And again, the only thing that is a little bit different here in this notation is that this SJT is household J's share of aggregate savings. This capital omega T is the aggregate economy share of savings. And so this is just algebra here. We're not doing anything other than algebra. This is the budget constraint of the agent. And this is really kind of crucial that we can write it this way. So this is a depiction of what's happening in the aggregate economy and what's happening in the agent's problem. So the aggregate economy, you're getting output that's being allocated between capital and consumption. And the share that goes to capital is this capital omega T. Then you go into the next period, what you get hit with is you get hit with an aggregate technology shock, and then you make this aggregate savings consumption decision again. So you get hit with the aggregate technology shock, but you also get hit with an idiosyncratic shock to your labor that determines your aggregate labor. So what's the household doing? The household is getting, so little omega is the household's share of output that they walk into the period with. So this is their wealth. So omega T, little omega T times YT is household J's share of the wealth. And then they're going to save some S. So I've eliminated the J subscripts, but they're going to save some SJT of the aggregate, which is omega T. And then they're going to get a return, and the return is alpha ST, which is the return on their capital holdings, and 1 minus alpha ET. And again, this is just reformulating the economy in terms of shares. So this is, again, just a little bit of algebra, and now I can write the economy in terms of shares of output, which I think is pretty useful. So why is that useful? Well, I'll tell you why it's useful in a few slides. I want to talk a little bit about the uncertainty, which I haven't done yet. So the uncertainty here is going to be very standard, and this is where I think the mathematicians are kind of playing a really important role. So what I wanted to do is I wanted to assume that we had Markov shocks, the same as in Krusell-Smith, the same as in Arigari, and they convinced me that we can actually do something a little bit more general than that. And so what we did is we just assumed that there's some bounds placed on these shocks. So the aggregate technology shock that's going to hit production, we're just going to assume that it's big O of 1. So this is big O notation. And that just means that it's some constant that's going to be finite. It can be any constant that you want. It's going to be positive and finite. The idiosyncratic shock EJT, we have an assumption on that. And the assumption is that with some probability, some positive probability, you have unemployment. So that's what this equation says. So the probability that EJT, which is the agent J's employment shock, is equal to 0 is some lower bound. So there's some lower bound. So this is the opposite of kind of big O. It just says that there's some positive probability that you're going to be unemployed. That's all that equation says. But we're not putting any other restrictions on the employment shock. They can be Markov, they can be whatever, normal. So this is going to nest, these assumptions are going to nest basically everything that's in the literature right now. The last assumption that we need, and we only need 3. The last assumption that we need is we need that the idiosyncratic shocks. So what we're gonna do is we're gonna have a set of these agents, a subset. So right now they're in households, and what we're gonna do is we're gonna subdivide these in households into subsets, 1 through S. And for any J and K that's in the same subset, so you have 2 households that are in the same subset, their distribution of not just current, so here it's a little bit misleading, the slide is, it's not just their current employment shocks, but their future employment shocks have to have similar lean processes. So what does that mean? So we call this similar future prospects. So ex ante, if you have 2 households that have the same level of wealth, the same savings, same consumption, then their employment shocks cannot look drastically different. That's what this assumption says, that we have to be able to subdivide these in households into these subsets. And if you're within the same subset of another household, then your employment shocks ex ante going forward have to be the same. So what does this rule out? So this rules out kind of what we call favored agents. And if you have favored agents, that just means that you have 2 households that look alike in terms of their current wealth, but one household has a very different future employment shock sequence possibility. And if you have that kind of assumption, then getting aggregation the way that we're going to get it is going to be very hard. So this is going to be a way to actually break aggregation. And something that we're going to talk about in future papers is this assumption is really what's crucial for generating aggregation in Krusell-Smith-like settings. It's that agents have basically the same distribution of shocks, of employment shocks, as all other agents that are in their kind of wealth category. If you break that assumption, then you're going to break aggregation. So our assumptions are very general. They rule in Krusell-Smith.
Thank you very much, Todd. I open microphone for everyone, so if anyone would like to make a comment or ask a question directly, you can just enable your microphone on the top part. So, Todd, just to understand what these codes that you are making available and eventually will be doing is you can solve for the
one thing that we did in the papers to show this,
taking into account the heterogeneity.
The aggregate. So I
but
just
the end
walked you through the algebra,
of the day, you
can back.
or you can both. You will have mention both of the aggregates
Appreciation.
of the
You have incomplete depreciation. So what we do is redefine an aggregate, call it Y, which is equal to aggregate output plus some level of unappreciated savings. And Y tilde we know is going to be bigger than Y. And then you just rewrite the effective labor shock, call it E tilde J, as EJ over times Y over Y tilde. And we know that the labor shock is going to be less than, so E tilde is going to be less than EJ. So this is going to satisfy all the conditions on the shocks that I just mentioned, and it's going to more about changing the depreciation.
can you error
Aggregation.
uh,
Some number less than one. So yeah, yeah. Households
having negative sir. And therefore having a different result for the error
the firm.
term.
So I lose